Hello, I hope I'm audible. I'm gonna go ahead and start my presentation now. So yeah, I've been really looking into a bit of custom memory allocators in C++, what they are and how they work a bit. So yeah, I just wanna start with saying that all my images are stolen from the internet, so please don't share this. I don't wanna get in trouble. So, what is memory in a computer and how does it actually work? Well, memory is a fundamental part of computers as we know them today. It's used to store and retrieve the data that we need in order to execute instructions in a computer. So, if we didn't have memory, we would actually have to reconfigure the whole computer in order to change its behavior. So, memory can actually be in a wider range of different media that we don't really think of as memory but more as storage, perhaps. Some like magnetic tape, for instance, to spinning magnetic or optical discs. Just checking so I was audible. Yeah, so these types of storage are actually called secondary memory or mass storage. And yeah, I was really gonna joke about the storage capacity of a magnetic tape when I found out that Sony announced last year that they developed a new tape storage technology. Could store freaking 330 terabytes. Thanks, Sony. So yeah, I mean RAM is what we most commonly think about when we think about memory in a computer, and it's called primary memory. And as you can imagine, it's way faster than all the other memory. So yeah, we have a diagram how fast memory is here. You probably just add a big cone shape here for Sony. There you go. You're welcome. But yeah, my point is really that memory is not created equal. Some memory is much faster than other memories. So, I mean, there's a lot of that you can learn about memory, and I mean it's really good to know if you're gonna work with it. So I dove a little bit deeper, and oh, turns out that processors only can read word-sized blocks. I'm like, word? What size is a word? And yeah, turns out that it is actually dependent on your processor. In today's computers, it's usually 32 or 64 bits. So yeah, and then data in memory should be aligned probably to these word-sized blocks that it can read. So if you take a look on especially this right example, you can see that the data doesn't actually stretches over two sized blocks. So the CPU would have to read both of these blocks of data and then mask out the data that it actually needs, which is quite more cost expensive than just having it aligned to begin with. So yeah, there's actually a whole lot that goes on with this. So I'm gonna make a few statements. Look at this, interactive. So the size of a structure is a multiple of the largest types. So if you, for instance, have a structure with a data type that's 4 bytes big and one that's 8 byte big, the whole structure will need to be a multiple of the largest data type, which is 8, and the closest multiple of 8 is 16. So a structure with these two in it, even though it's only 12 bytes, will have to be 16 bytes. And the alignment of the structure has to be the same as the largest data. So in this case 8 as well. And memory address is a multiple of the data size. So if you want to store an 8 somewhere, oh, I don't have the pen. You obviously want it to start on a good address. That's like 0 or 8 or 16 or 24. You don't want it to randomly start on like address number 3 or something. So yeah. And then you also want to ensure something called natural alignment, that they actually start where they should start. In order to do that, you may have to insert padding between structures. So if we, for instance, put this nice 4 bytes into my structure, in order to store this 8 byte, which needs to start on an address that starts with, that's a multiple of 8, can only start here or over here. So between this space there'll be some padding, and the alignment of my current structure will be 8, but the total size will be 16, even though I'm only storing 12 bytes in here. So if I, for instance, put down 1 byte, and then I want to fit 2 bytes in here, I need to put them over here, because 2 bytes needs to be aligned to addresses of 2. So there'll be some padding in here, and some in here. So what I have now is I have a structure with an alignment of 2, because that's the alignment of the biggest data type in here. But the size of the structure is 8, even though I only have 6 bytes in it. But we can clearly see that I could probably fit it in 6. So then there's something called packing, which is actually the act of reordering data to reduce the packing. So if I were to pack this, I could probably move the 1 over there, 2 over there. Now it's totally 6. Perfect. So yeah, I have a little a little viewer question. So if we take this nice structure that I have here on the side, it has an A and B and C and D with different sizes. The A has the size 1, B has the size 8 bytes, C has 2 bytes, and D has 4 bytes. So if you want to participate, you can just type your answers in the in the chat. So the questions are: what would the alignment of my structure be with these data types in it? What would the size of my structure be? And what could the smallest size of my structure be if I were to maybe reorder them? So yeah, something to think about if you want to. I'll go over it in the end. Okay, so let's talk a little about actually allocating memory. As some of you may know, there's a stack and a heap that you always talk about when you allocate memory. The stack is built from the bottom and up by stacking things on top of each other. And it's a last in, first out type of queue. So if you imagine if you had like a tube of marbles or something, if you put marble in, the first marble that will come out is the last one that you put in. So like that, you can only push to the top and pop things from the top. So you can't add or remove something from the middle or bottom. So yeah, I mean it's a really simple structure, but it's really fast at accessing memory. Oh, yeah, I guess I can do a short example. So you'll get a chunk of memory assigned to the stack. This is stack, obviously, they look like that. And the stack will actually keep track of both where you are in the execution of your program, but also it's kind of dependent on where you are in a scope. And a scope is these curly brackets. So when you go inside a scope, you're often inside these curly brackets. Then when you leave them, you're outside the scope. So for instance, it will store where we are in the program. That's obviously where we are. They'll come down here, enter a function. Let's just call it f, because I can't write. You'll move down, get into the scope of this function, come, and it will allocate a variable called a on the stack. Boop. Push it there. Assign it the value of 5. If you can read that. Keep on moving down. Do the same with B. Push a B there. Value 10. And then it will exit this current scope. And what will happen is that everything that was inside this function scope will get popped. So B is no more, and A is but a memory. And yeah, the function will be popped as well. And since we knew exactly where we were before, we can just continue the execution. Boop, boop. And yeah, if you actually, the size of the stack is quite small, so it's quite easy to go over the size of the stack, store more stuff than you can. You get this really famous Stack Overflow error, which is also incidentally the name of a really famous programmer web page where you can look up all the good things and bad things about code. Right, so the heap is the second part of this. Unlike the stack, it's totally unsorted. You can access all the data in it at any time, and you can add and remove data wherever you want, pretty much. So to store something in the heap, you must first ask for memory. Then when you get it, you're pretty much free to do whatever you want. But you still gotta be careful, because if you use it wrong, or like try to use too much memory or something, bad things can happen. And finally, when you're done, you gotta free your memory, return it, because otherwise you'll end up leaking it, and that essentially means that the OS won't get its memory back, and yeah, eventually bad things will happen if you run out of memory. And yeah, asking for this heap memory or later freeing it is actually a relatively slow process. So not slow for us, but computer terms, relatively slow. So how do you do this magic heap allocation? Well, turns out there's a few ways. First way is malloc, stands for memory alloc, comes from the old C language. Quite easy actually, it just takes the size that you want to allocate, gives you a pointer to that piece of memory, which later have to be released with a free call. In C++, they introduced a new operator, which instead of taking the size that you want to allocate, it wants to know what you want to allocate. So you give it actually an actual type of an object. For instance, you try to make a new player or something. You give it that, and then new in itself will check up what size the player is, and it will allocate that space from the heap, and then it will also create the actual object for you and return that. And yeah, you don't wanna malloc memory and free it with delete, or allocate memory with new and free it with free, because then some bad things can happen. So you don't wanna mix that up. Right, so small example of how this can look. So again, memory is assigned to a stack, and a magical heap, draw it as a cloud, seems appropriate. And yeah, nice. Oop. So we actually start up here. Perfect. So what this does is this actually creates the asterisk here actually means that it's a pointer. So this is gonna point to a memory somewhere, but for right now it only creates the pointer, let's call it Peter, pointer PTR on the stack. So we're still on the stack. Moves down here. Here we can recognize the new call, which will actually ask the heap for memory to fit an integer. So somewhere in the heap, over here, there was some free memory that now PTR will actually point to, because it's a pointer, points to memory. then we might maybe want to store something in that heap memory. So we'll ask PTR that at the place where you have your memory, save a 10. Perfect. And then we go on and we are responsible, so we delete our pointers. What will actually happen is that this box that says that this was allocated memory disappears. But PTR will still point at exactly the same address in memory, and the 10 might still be there, but you can't be sure because at the moment that you free it, somebody else can take it and write some other junk in there. So you don't want to use PTR after you actually freed it, so there's usually set it to be a null pointer or null, meaning just that it's intended to be nothing. So yeah, if you just compare them, the stack is really fast, heap is a little bit slower. On the stack, static memory, it's on the stack stuff that we already know when we compile the program will be stored, and from the heap we will have something called dynamic memory. For instance, you may not know how many times a player will click in your application and spawn a sprite every time. So then you maybe want to allocate dynamic memory every time he clicks. And the stack is actually very limited in size. It's usually just a couple of kilobytes or megabytes. Can be increased though, but it's very small. And well, the heap, you have your whole RAM, and then you have some virtual memory, so you can actually have your normal storage media become sort of heap memory as well. And yeah, stack is popped when it goes out of scope, so it'll die by itself, but the heap won't. It'll stay there until you kill it, and if you don't kill it, you'll leak the memory, and it'll be there until you restart your computer. So yeah, gotta be responsible and delete your memory. Yeah, so this is C++ introduced a bunch of new operators. So there's new operators and delete operator. Then there's also the same but for arrays. So there's just a bunch of stuff here. But we want to look at this new operator that we have been using. Internally it actually calls something called operator new, which, like malloc, just takes the size, gives you raw memory back. Then it does something called placement new, which actually creates an object for you. So why is this important? Well, it's because using this we can actually separate allocation and creation or construction of objects. Because we're looking at memory allocators, we don't specifically want to create objects, we want to manage memory and then maybe later create objects. So yeah. Right, memory allocators. What do they do? Well, glad you asked. The job of a memory allocator is to manage memory, as fancy as that sounds. But yeah, it's mostly dynamic memory that you allocate from the heap, but you can also manage memory from the stack. So how it usually works, in just general terms, it gets a really big chunk of memory in the start of your application. This is quite time consuming in computer terms. And then during the runtime of the application, you don't allocate any more dynamic memory. You just ask your manager for a little piece of that big chunk, which in comparison is super fast. And then when the application is over, you free this big chunk, give it back. So why would you want these? Well, I'm actually gonna start backwards and list a few examples why you maybe wouldn't want these, because you don't really see these in every type of applications. They have their niche target. Oh yeah, first of all, I mean, it's quite complex, especially if you're gonna write them yourself. You really need to understand like how they work. Maybe you don't really have that much need for speed. If you don't do that much dynamic allocation, or if you don't trying to crush the 60 FPS mark, it's probably okay to not probably okay to have a few frame drops. Yeah, I mean, really it's prone to errors and get hard to track down crashes. Because I mean, just working with memory is hard. If you're now gonna manage the memory that you're working with, yeah, fun. So, yeah, I mean, these are just some bad things. There's a lot of compelling reasons why to not use custom memory allocators. But obviously there are benefits, because I mean they are used, and as you can imagine, the biggest benefit is more speed. So I mean, these guys, malloc and new, that you use to allocate memory, they are really good. I mean, they have been really much optimized, but they are really good for a general purpose of allocation. So they're good for a lot of allocations, but they're not the best one for each and every allocation. So this gives you the benefit, since unlike the allocator, you know exactly when and where and what and in what context you need to allocate. So perhaps you don't need thread safety, so you can totally skip that and get some more speed out of it. And yeah, it can help you think in data-oriented design, because you're constantly actively thinking about how data is stored in memory. So, just to bring up a few examples of some allocators. This is probably the simplest allocator that you'll ever see. Basically allocate a chunk of memory and give it to the allocator. Then you have a pointer to the start and a pointer where you're at. When you allocate, you check, oh, can I fit this allocation? Or if you had 100 bytes and the allocation is 20, you say yep, and you move the pointer 20, and then you allocate some more, and then some more. But in this one you can't deallocate. The only thing that you can do is actually clear or reset this whole allocator. So what you do is just you take this and say, I'm gonna point at the start again. Now all my memory is free. And this is actually super useful if you're trying to, if you only need memory from like frame to frame. So if you need to return something in a function and you just need some dynamic memory for a short period of time, you can just use a linear allocator. Or if you need for like the entire runtime of your application, and then divide the memory into separate other managers. The stack allocator, as you can imagine, works like a stack, pop and push. You can obviously also add clear to it. Something that's pretty interesting with a stack allocator is that when you deallocate stuff, it will actually be deallocated in the reverse order. So for instance, if you use it as a level loader, when you load in the level, you'll get it in one order. Then when you unload the level, it will be unloaded in the reverse order, which is usually what you want. Free list allocator, it's a linked list of blocks of contiguous memory. So when you try to allocate, let's say you want 4 bytes, it can look through all the blocks and say, hey, this small block right here fits you perfectly. And it gives you it back. And then when you deallocate, it will try to put blocks back in and try to merge them again. So you can use a bunch of different strategies. Another popular is the pool allocator. It's like the previous, is a linked list, but all these blocks have the same size. So this one is if you're going to allocate a lot of the same type of objects, fixed sized. Because if you know exactly what type of objects you need, you know that it'll fit in one of these. So what you can do is, when you allocate, you always take the first one, give it back. When you deallocate, you just put it first in the queue and make it point to the next one. So it's quite fast in that way. And yeah, composition is a big thing in allocators. It means combining allocators, putting them on top of each other or bucketizing them, and like depending on, so if you have a lot of allocators that work really well for a different range of size of allocations, you can just bucketize them. And like fallback allocator takes in two allocators, A and B, and then you try to allocate. It tries first with A, and if that doesn't work, it tries with B. Yeah, there's a whole lot of that you can do with composition. So, lastly, I'd like to just go over some memory allocator features, mostly in terms of like debugging, where it's really useful stuff that you can add. And these things are actually, you can set them per allocator, so allocators can have different features. One is like bounds checking, making sure that nothing goes out of bounds, which shouldn't be. You can do it by adding like magic numbers at the start of the end, and then every time when you free memory, you'll just look at the numbers, make sure that they're still there. If they aren't, something has been writing outside of its bounds, going outside, and then you can actually like turn it up a notch and do some serious bounds checking. So for every time you allocate or deallocate something, you can go over every allocation in that allocator and look at all the bounds. So yeah, that's pretty useful. Memory tracking, like simply just keeping count how many allocations you do and how many times you deallocate. So if you find out that, hey, my program is closing now and I have 3 allocations still left that was never deleted, then you can turn this up a notch and also store the file name and the line number of the one that made the allocation, and you actually store it just together with the data where you allocate, so you can just read it out. Oh, it's from this file. Or you can just store the entire call stack. But this is obviously super computational heavy, so you just want to do it when you are sure that you have a bug and need to track it down. Memory markings, really popular. Is using cool hex speak to mark certain addresses. For instance, if you have a pointer and you look at it and it says that you got some bad beef, oh, you know you done goofed. Yeah, but this is quite useful. Thread safety. If you can set this per allocator, because I mean most allocator will never have to be thread safe, and you can actually gain a lot of speed because there's no overhead. And for those who need it, can obviously have it. And lastly, the actual location of where you store your memory. Normally you store it on the heap, the big magical cloud. But there's no reason why you can't allocate a big array and just store it on the stack, because it's much faster. So, if somebody wanted to see how it works or make a guess, I guess it's too late. But if you have any other questions, you can probably ask them now and I'll answer them later. So how this actually works. First we want to know the alignment of my structure. So just the size of everything is 1, 8, 2 and 4. The biggest alignment in here will be this int64, which has an alignment of 8 as well. So the alignment of this whole structure is 8. If you're gonna look at the size, so let's see, we first have a single byte. Oop. Then we have an 8 byte, but 8 bytes can only be aligned to memory address of 8. So if we have 0 here, we have 8 here. So then the 8 bytes will be stored over here. There'll be a lot of padding here. Then comes the 2 bytes. And then the 4 bytes. And 4 bytes can only be aligned to addresses that start with 4. So it'll be 2 more padding here and then the 4. And a size needs to be a multiple of the largest data type. So in this case, we're up at 24 bytes for this structure. And the smallest one that's possible is if you put the 8 bytes first, then the 4 bytes, then the 2 bytes, then the single byte, and you just have one single padding in here. You can actually get it down all the way to 16 and save some memory. Yay! Or like use a union and just use one of them at a time, but yeah, that's beyond the scope. So, thanks for listening. I haven't been able to read anything. Totally focused on my presentation, so let's see if anyone asks something. Well, thank you everyone. Yeah, thanks for listening.